Hello everyone, welcome to this lesson on the quotient of powers property of exponents. Okay, so let's consider 3 times 3 divided by 3. Well, we could certainly go ahead and say 3 times 3 is 9 and divide it by 3 and get 3. But we could also go about this by thinking that we've got 3 on top and bottom. They can cancel or form a 1. And so we are just left with 3. Um, And so we had a factor of 3 in the numerator, factor of 3 in the denominator, gave us 3 at the end. Yeah, 9 divided by 3 is 3, but we didn't even need to do that. When it gets a little larger, we might see more benefit in this strategy here. So we can see 3's in the numerator, 3's in the denominator. Well, let's start canceling them out. So every time we cancel, it's really a 1. It's 3 divided by 3 is 1, 1. 3 divided by 3 is 1. And we have two factors of 3 left in the numerator. So 3 times 3 is 9. Terrific. So doing that prevented us from having to figure out what the number of 3 times 3 times 3 times 3 times 3 times 3 actually is. We could have also thought about this, though, as it started off as 3 to the 6th power over 3 to the 4th power. That's kind of interesting. Let's hold on to that, and let's look at another example. Whoa, that's a lot of 3's all over the place. How many do we have? In the numerator, we really have 3 to the 11th. In the denominator, 1, 2, 3, 4, 5, 6, 7, 8. 3 to the 8th power in the denominator. And we could go through and, cancel them all out, but you should hopefully be able to recognize how many more are going to be left in the numerator before we even do that. There's going to be 3 left up there. So our answer is 3 to the 3rd, which we could do, and that's just going to be 27. So you probably picked up on the rule as we did that example there. We had 11 up top, 8 on the bottom. It turned into 3. So if we're assuming that m is a number and it is bigger than n, well, if we have x to the m divided by x to the n, what that really means is we have a balance, like the same number. If we lined up equal number of factors of x over each other in the numerator and denominator, this first part of the fraction is kind of all going to cancel out. There's n number of x's that are going to cancel from the numerator and the denominator. If I compare this to the example up above, there were 6 up top, 4 on the bottom. So it's like there's a group of, we could have put 4 factors of 3 all together in kind of a first fraction, and then multiply that by however many were left over just 1. And so in the example above, there would have been 2 factors of 3. But if we don't explicitly know there were 6 of them and 4 of them, if we just had m and n, how many factors must be left over? Well, that must be m minus n factors that were left over. So this leaves us with m minus n factors of x, and our rule says that this is our exponent, x to the m minus n. So then, if we have x to the m over x to the n, and m is bigger, we have m minus n as our exponent. Terrific. Let's actually see this work out in some examples. 2 to the 5th over 2 to the 2nd. Well, we can subtract the 5 minus the 2. Notice they have the same base of 2. So we can subtract them with our quotient rule, and 5 minus 2 is going to give us an exponent of 2 to the 3rd, which we know is 8. And that's our answer. If it's 3 to the 9th over 3 to the 7th, we can apply the quotient rule because we have the same base, 3, raised to 2 different exponents. So we have 3 to the 9 minus 7. And 9 minus 7 is, of course, 2. And so this is 3 squared, which is 9. We never even needed to know what 3 to the 9th was or 3 to the 7th was. That would have been a lot harder than using our quotient property. All right, if we just have variables with exponents, we couldn't even evaluate them if we wanted to. So we have to use our quotient property. So x to the 5th and x to the 2nd, that's 5 minus 2 is x to the 3rd. Okay, now when we look at example number 4 here, we have the same exponents, but they've been flipped. And so we totally could do this just following the quotient rule exactly as it looks and say that this is 2 to the second power, which is the exponent in the numerator, minus the exponent in the denominator, which is 5. And so 2 to the 2 minus 5 would give us 2 to the negative third. We can't leave negative exponents, we know that already, so we'd make it 1 over 2 to the third. But, we should make that 1 over 8, but I'm going to show you another way without having to get into negative exponents at all. So let's go ahead and look at this next example, and I'm going to show you my personal trick for how we would approach a situation where there is a bigger exponent in the bottom. We kind of jump right from the start down to about this step here without having to go through some of those in-between steps. Okay, so here, 7 to the 8th over 7 to the 9th. If we were to write all the 7s out, there'd be 8 7s up top, and there'd be 9 7s in the denominator. So we know that there's more factors of 7 in the denominator. So if we started canceling, we're going to cancel basically every one that they have in common, but there's going to be how many more left over? Well, 9 minus 8 would tell us how many left over, but where are they going to be left over? Not in the numerator, because there wasn't as many in the numerator. There were more in the denominator. So I'm going to still do 9 minus 8, get the positive 1, but that's going to go in the denominator. Can't leave the numerator empty, so we got to put a 1 up there. That's our answer, 1/7. Let's look at some more. Here, bigger exponent in the denominator. If we looked at all the factors of x and wrote them all out, we'd cancel 4 of them out in the numerator, 4 of them out in the denominator, but there'd be more still left in the denominator. How many more left in the denominator? Well, we can take the 8 minus the 4 and recognize that there's going to be just 4 left over in the denominator. Got to leave 1 in the numerator. Terrific. 2 to the 5th over 4. Well, they aren't even like bases. Haha, but we have some tricks up our sleeves. We see 4, and we're looking at the 2, and we're like, how can we make this all work together? Well, 4, of course, is 2 squared. Now they are same bases raised to different exponents. We can apply the quotient property. Could we have evaluated this without doing that? Sure, the numbers are small enough, but when the numbers get bigger, it won't work out as well. So we subtract the exponents, and we realize that's 2 to the third, or 8. All right. Let's take a look at another one. Ooh, yeah, some negative exponents. Ooh, so negative exponents. We totally could apply the quotient rule just as it looks. And we would have, and I'll show this both ways, 2 to the negative 5, that's the numerator's exponent, minus, because that's the rule. The rule says we're going to subtract the exponents. But then the denominator's exponent itself is negative. So it's negative 5 minus negative 2 is the exponent. Well, when we subtract a negative, we know that that means we really need to add. And so we have negative 5 plus 2, and we could totally do that and say negative 5 plus 2, that's going to give us 2 to the negative 3. So 2 to the negative 3, we can't leave it like that. We're really going to have to make this 1 over 2 to the third. And 1 over 2 to the third is 1 over 8. But if we look back at 2 to the negative 5th and 2 to the negative 2nd, that's so confusing to me. I'm going to apply the negative property of exponents first and rewrite this as 2 to the positive 2 over 2 to the positive 5. Now we've got positive exponents. And now I'm still going to apply my little trick where I'm going to look at where the larger exponent is. And the larger exponent's in the denominator. So I'm going to do 5 minus 2 is 3. Where is that going to end up? On the bottom, in the denominator. So it's 2 to the third on the bottom, put a 1 up top, and we have 1/8. So that would be my preference for how to do that problem. There's nothing wrong with doing it the other way, but to me, I'm going to make less mistakes doing it this way. All right, let's look at another example. Let's find a real fun one here. Ooh, 13. Everyone loves fractions. So we've got 2 to the third over 2 to the third of the fifth over 2 to the third of the second. Well, fractions are fractions. Fractions are just bases. It's the same base with exponents. So we can apply our quotient property and say this is 2/3 to the, Well, 5 minus 2 is 3. And we can recognize that that's going to be 2 times 2 times 2 over 3 times 3 times 3 is 8 over 27. All right, when we look at number 15, however, we're like, look, the bases are different. We've got 3/2 in the numerator and 2/3 in the denominator. Those aren't alike, so I guess we're done. We can't combine them. We can't use the quotient rule. I know you got excited about that, but guess what? We have a few tricks up our sleeve. Since you probably noticed that they are reciprocals of each other, we have things we can do with reciprocals. If we take the reciprocal of the fraction, that's going to cause the exponent to change sign. So I'm going to leave the numerator as 3/2 to the 5th. The denominator, I'm going to turn it into 3/2. That'll make it the same base as the numerator, but since I took the reciprocal, I have to change it from a positive 2 to a negative 2. Wow, how about that? Now, I could subtract 5 minus negative 2 and recognize that's 3/2 to the 7th. Or the other thing I could do is I could say I'm going to apply my negative property of exponents right now, take the 3/2 to the negative 2, and carry it up to the top and make it 3/2 to the positive 2nd. I'm going to go ahead and do that personally. It doesn't really matter. Either way would be equally correct. But when we bring it up to the top, now we have 3/2 to the 5th times 3/2 to the 2nd. And now, if we apply our product property of product of powers property, and we realize we have 3/2 to the 7th power now. Terrific. And we'll leave it like that. We could probably do 2 to the 7th there, but we'll leave it like that. All right, let's look at, this looks like fun. Who loves 1/4 the negative 5th? Well, 1/4 negative exponents. You should always be thinking negative exponents and reciprocals. And you know what? I can kill 2 birds with 1 stone. Why are we killing any birds with stones? I don't know. But if we flip the 1/4, it'll be 4, and it'll turn the exponent positive. So, hey, 4 to the 5th, that's so much better than 1/4 in the negative 5th. We can do the same thing on the bottom and make it 4 to the 3rd. Hey, quotient property time, same base, different exponents, subtract them. 5 minus 3 is 2, 4 to the 2nd is 16. That was awesome. All right, let's go get something real fun. Oh, yeah, look at that. 2 to the 3rd, x to the negative, let's not even read the whole thing. It's long, but we're going to look throughout for some common bases. So I'm looking through. I see an x there and an x there. Terrific. I see y and y. Also good. I see these coefficients out front. They don't have quite common bases yet, but you probably are onto something that we probably can make something happen with that 4. Well, that 4 is 2 squared, right? So 4 is 2 squared. Great. So, but then we have really 4 squared. We don't have just 4, we have 4 squared. So that's like 2 squared squared. We're kind of getting a glimpse into a lesson coming up here, but we can still think about this. That's the 2 squared, that's the 4. So that's how they're the same. It's the same thing inside, same exponents. Well, 2 squared squared, that means 2 squared times 2 squared. Whoa. 2 squared times 2 squared. How many factors of 2 do we have? We really have 4 factors of 2. Whoa. That was a lot. 4 factors of 2 means it's 2 to the 4th power on the bottom. So 2 to the 3rd up top. I'm going to move the x to the negative 8 up as x to the 8. Y to the 42 right there. On the bottom, I'm going to rewrite that 4 squared as 2 to the, let's keep it as 2 to the 2nd to the 2nd, even for a second. We'll slow it down there. And now we've got x to the 4th from the numerator coming down and y to the 24th. Hey, no more negative exponents. That's a good start. So what else can we do now? We've got some variables with the same base. We got some same bases with different exponents. So let's just draw ourselves a fraction line here. 2 to the 3rd, x to the 8th, y to the 42nd, all in the numerator. Let's just handle this. Actually, I take it back. Let's just handle this 2 to the 2nd, 2 to the 2nd. What can we do with that again? Let's really write this out just so we're very clear on where this came from. That's going to be 2 to the 4th. That's 4 factors of 2. All right, let's copy down the rest. X to the 4th, y to the 24th. Terrific. All right, now we've got lots of things with the same base in the numerator and the denominator. That is triggering quotient rule in our brains. And we're like, yay, quotient rule. We can apply it 3 different times. Hurrah! We can apply it to the base 2's, to the base x's, and to the base y's. All right, 2 to the third over 2 to the fourth. We subtract 4 minus 3. There was more on the bottom. So let's throw just a 2 to the first power. We don't need to write the first power, but it's on the in the denominator. X to the 8th and x to the 4th. Hey, subtract those. We get x to the 4th. It's going to be in the numerator where there was more factors of x. And y to the 42 over y to the 24. There are, in fact, 18 more factors of y. Where are the 18 more factors of y? They are in the numerator. So that's what we put. Oh, I was color-coding there. Yeah, sort of color-coded. Okay, great. Y to the 18th. And that's our final answer. Terrific. Don't you feel happy about that answer? I hope you do. I do. It was a great answer. Thanks for checking in with us. Stay tuned for some more examples in a follow-up video. And I hope this helped.